Consider this example that we have three functions or subroutines of between a, b and c, and they are called each other in a nested fashion. If you check, we can see that call and return occurs in a stack-like order. The most recently called function is the first one to return. So when in the program we call jump and link b, it means that we call function b, the return orders should be saved somewhere. I put it inside the stack, so it will be in that end of the stack. Then we jump to the start of the rest of the subroutine b and start run it again. This subroutine called subroutine c or function c. So again, we need to assert this return address in some place. So it should be in the top of the previous return address. Why? Because when we return back from the subroutine C, we want to return to this one, not return to the subroutine. So I have to retrieve the last return address that I saved. So it is completely useful to use a stack data structure here. Is used or reserved for a stack, and we have a special register $, ESP a stack pointer, but we don't have push or pop instructions in MIPS assembly language. So you have to write or implement these operations by using the stack pointer and increment for unit, or decrement per unit in order to push and pop or update the stack pointer. And by using load and store, you can pop one element or push one element in the stack area. Implement the push function or push method of a stack. We should move the stack pointer down to make room for the new data and store the element into the stack. Assume that we want to store the content of register T1 and 2 inside the stack. So this is the initial version of the stack before we push something. And after that we want to store, say, the content of the T1 and T2 are stored here, and the stack pointer should be updated to point to the top of the stack. This is the top of the stack and stack rows downward. So this is the end of the stack and this is the top of this time. So this is the way that we can perform it. First, we add 8 unit to the stack pointer. So it will become to this point, and then we say that inside the a store-bought registered to 1 into this location. A stack pointer plus 4. So a stack pointer is here. A stack pointer plus 4 should be here. So PT1 will be a store in this one in this world, and the next is toward a store. The content of T2 into the location that a stack pointer point to this one. So it's like winter is here because I add 8 unit to the stack point here, and now it is the point that a stack pointer point to this location. I can save the PT2 here. Also, it can be write by this way. Both of these codes are equivalent in order to pop the elements from the stack. The procedure is the reverse of the cushing. Assume that I want to hop the top of the stack and put it inside the $, as 0. So I should write load. What $, is 0, 0 stack pointer. The top of the stack will be retrieved and stored here. Or in this example we want to retrieve this one, but it is better to always pop the top of the stack instead of accessing the other elements. So in order to pop the top of a stack, it should be 0 here. And after that I should update the stack pointer. Move the stack pointer to this point by add 4 unit to the stack pointer. I can come to this point and now the T1 is the top of the stack and this element is removed from the stack. You are an example of using function in MIPS assembly language. Assume that you want to write a program to read one number from the keyboard and print its factorial on the screen. Let's first focus on the factorial. This is the function that I want to implement. This is the factorial function. It's received one argument and we need to initialize a variable, for example, f by number 1. Then all of the number between 1 to n should be multiplied to each other to find the factor here. In this example, the loops start from the n and it's incremented 1 unit every time and I multiply by the f and the result is stored in the f. After this for terminated the value of the factorial is inside the f variable and we return it to the color program. Let me show you. How can I implement this algorithm in MIPS? This is my factorial function. I wrote it after the main part. $90 initialize with 1. This is corresponding to the f variable inside the algorithm that I mentioned and $91 is corresponding to the I in the above C code. There is a loop here. Check the value of the counter. Is it greater than or equal to 0? If it is equal to the 0, we should go out. But if it is greater than 0, we come to this line and we multiply the value of the counter T1 to the f and the result is stored inside the T0. This is another multiply instruction in the MIPS. The previous multiply instruction that I mentioned in the previous lecture only accept 2 parameters. But here, as you can see, there are another version. This version only multiplied these 2 parameters and the result will be a store inside the first parameter. After this art perform, we should decrement 1 unit from the loop counter and we come back and check the loop condition. So this is I minus minus in the C code. And this is the part that we should check that I is greater than 0. If it is, yes. If it is true, we continue. Otherwise, we go out here. We say that if it is 0, go out. Otherwise, continue. After we compute this factorial, we should put it inside the $sign with 0 because every function returns their value to the color function by register with 0 and in order to return the use jump register and we always use $sign or a return address. Take the main program. First I prompt a message and ask the user to enter a number. And here I read one number from the keyboard and a story inside the variable number that I declared here. Also I printed on the screen because I want to show a message like this. 5 factorial is 126 factorial is 720. So I want to show the input number. Then factorial is message and then the result. So this is only part of the program to print the input number on the screen. Now I print this message factorial is, so it will be something like 5 factorial is. And now I should compute the 5 factorial. The input number is inside the number, so I should put it inside the registered $sign. A 0. Because all of the function in the MIPS receive the parameters from the registered $sign a 0, a 1, and etc. Now, I called the factorial function for this purpose. We have an instruction jump and link. Jump and link fact it saved the return address into the $sign or return address register. And then it will jump to the fact label and execute this part of the code. After we return back to the color we are here and the answer is inside $sign with 0. I want to print it on the screen. I should put it inside $sign a 0 and call system call number 1. And finally, since this program consists of a function, I have to use a specific system call to terminate the execution of the polygraph system. Call number 10 is exit system call. So when I run the program, it starts from this line. And when it switched to this point, it will be stopped. If I didn't write this code after this part, the system come to this line and without any reason the factorial function execute again, which is not correct. So let me run it. Enter a number. For example, 6 factorial is 720.